Y'all here? Look at, we've seen a couple of different kinds of isomers so far. Okay, let's take a look up here. We got these kind, where I've got, what's this guy's name? Pentane, right? 5. Now, if I were to take a guy off of here and move him around and put him back and make a whole different compound, that is a different name. Okay, what is he now? 2-methylbutane. Y'all good with that? Why is that? What kind of isomer is that, Bailey?
Hang on.
What kind of isomer? Max? No. We're just getting them today. Well, they're right there.
Isomer units.
What kind of isomer?
Alkane. No,
An alkane. No, this is not making the cut. I just got to tell you.
It's a Monday.
It's a Monday isomer. It's a Monday isomer.
We don't know. Conformational Isomers.
No.
Yeah, we don't.
Gotta know this.
We'll figure it out like
Keep looking. You just drew them on the last 2 worksheets. Structural isomer. Okay? They have totally different structures. Alright? That's why they're a structural isomer. Now, so, by the way, this guy here, he's different than the one I had a minute ago. Pentane's different than 2-methylbutane. He's different in his properties. He's different about every way you could imagine. All right, different melting point, different chemical properties even. This guy here is exactly the same. All I'm doing is rotating one to the other. Remember this? What was this? What kind of isomers are these? Conformational. It's still that thing. And I could do a conformational isomer around any of these guys. And that's what we were doing for the last 2 worksheets, 3 worksheets as well. You know, if I chose this bond, could you draw the Newman projections of these? So we have structural isomers, we have conformational isomers. Now, the ones we're going to get today are probably the most difficult and the most amazing here. I want you to look at this guy, right? Look at him carefully. Look what he's bound around him. Turn that front light on, please. See the colors a little bit better, maybe. Because I've got different colors on these guys. All right? And now look at this guy. What colors are bound around each of these? What are the 4 colors?
black, blue, yellow,
Black, blue, yellow, and green. What's around this guy?
same.
So this is identical, right? Actually, they're not. Look at it. What does it kind of look like is in between each of these? I'm holding the blue one. If I were looking at a...
Like there's a bond.
in between, if there was... Are they? It look like they're identical, right? Let's try to superimpose them on top of each other. Let's line up the yellow and the green. What happens to the black and the blue? They're not, right. Well, we'll line up the yellow and the blue. And then the black and the green aren't the same. You know what they are?
Mirrors.
Mirror images, exactly. They're mirror images. Your hands are mirror images. They're the same, but they're a mirror image of each other, so you can't superimpose them. Okay? You can't superimpose them on each other. You might think to yourself, so what? They're exactly... How would I name this guy? I would name him the same way I would name this guy. As far as his structural formula, he's the same. But he doesn't have the same properties. And that's what I want to illustrate for you with a interesting little demo. You guys all probably have had rye bread. You know what rye bread smells like, right? You would never mix up rye bread with mint.
No.
Or would you?
No.
Actually, you would. And they kind of smell very similar. How about pickles? You know, pickles have dill in them. Like dill pickles. Dill. Okay. I'm going to pass around some dill, crushed up in here. I'm going to pass around some mint, crushed up in here. And I want you to also keep in mind while you're smelling these, rye bread. Keep that all in mind. And when you take a deep breath of these, smell of these, you'll notice there's a similarity between all 3 of these, which you never would have put together. We have mint in our chewing gum and lifesavers. We wouldn't put dill in a lifesaver. No one's going to have pickle flavored lifesaver or a rye bread flavored lifesaver. All right, but I want you to smell these as they're going around, and you'll notice there is a similarity between the two. You know why? They can turn that front light off for me, please. They both contain the same chemical. They both contain this stuff, carbon. Difference is, one of them is a mirror image of the other. That's the only difference between them. Take a deep breath of each. Keep in mind in the back of your mind, because I don't have any sesame seeds for the rye bread, which is what makes them smell like. Right. And if you take a smell of each of them back to back, there's a strange similarity between spearmint and rye bread and dill. It's weird, all right? But can you smell it? Anybody smell the difference? It's a similarity? Nikki, come on, tell me, help me out here. You know, think of rye bread while smelling that. Nobody smells it.
Hold on, wait.
Now, when it gets to Nikki, she'll fight. Well, she likes to argue anyway. So.
I'll tell you if he's crazy.
How about between those two things, which is dill versus spearmint? You do? You don't? Well, they do. But it proves something about, it proves anything, but it illustrates something about our senses. Our senses are sensitive to stereoisomers. So even the same exact compound has slightly different properties when they're arranged differently around a central atom, which is what I'm trying to illustrate here. And think also of rye bread. Nobody.
I kind of get it.
You kind of get it.
I don't think it smells like the bread, but they smell the same.
They do. But the crazy part about that, even those you would not have mixed up. I mean, nobody has pickled flavored lifesavers, right? But you do. They do have a similarity in some way, shape, or form. And if I had the rye bread here, you'd be able to smell that too, but I don't have any. You'd be able to. There is a similarity between those that you would not have thought of. All right. Okay. So these guys. So again, back to our. You can put them on the radio. Yeah, right over there. It's fine. So these guys are different. Let me show you why. They're not structural isomers. They're the exact same name as far as the arrangement of the atoms around this guy. Same exact name. 2,2-dimethyl, 3-ethyl, 4-chloro, whatever. Same guy. This is not. If I have a structural isomer, I have to break a bond, put them here. I've got pentane or I've got 2-methylbutane. Totally different name. They're not the same even about this. This guy seems to be a little bit more similar. Well, geez, that's kind of the same thing as this. But no, it's not. I can rotate this guy from one to the other. I cannot, no matter what I do to these two, they're different. I can't rotate one into the other. All right? And that, by the way, goes for larger. I'm using a very small one here. That goes for large ones like this, too. All right? They're called stereoisomers. Compounds with the same atoms and bonding that differ only by their spatial arrangement around a central atom. And that central atom is known as a chiral center. I'm going to, at the end of this, these notes here, I'm going to take a little bit of time and go over some of the conformational structural isomers you guys are doing on the worksheets here today. Because as I graded them, the three you already handed in, I was still not impressed by the fact that there were quite a few mistakes, despite the fact you had Beaker to help you out there with, and you had each other to help out when you're working together. Still quite a few mistakes on those. I wanted to go over them one more time. But if you thought you had to understand 3 dimensions for that, and you kind of do, have to understand 3-dimensional thinking for these kind of structural and the conformational, especially when you're drawing the conformational kind of in a weird way where you're looking down the bond. Well, these are 10 times worse. These are the place. Luckily, it's the last one. But this is where you have to think in 3 dimensions. You have to be able to see things in 3 dimensions. Because as you can see, these guys are identical. with very little difference between them. Okay, the only difference being how they're arranged in 3 dimensions around a central atom. No matter how I rotate these guys, I can't make them identical. Just realized the blue on the video looks pretty much like the black. I'm going to use orange instead. It's a little bit easier to see. That makes it a little easier. All right. So these guys cannot be made identical, no matter how I rotate them. And that goes back to large compounds, like the one you just saw, carbone, the stuff that's in. This gives, one of those 2 versions smells like the spearmint. The other one smells like the dill. Okay, and that's why they smell slightly different, but they have the similarity to them. There are other things that are also optical isomers. In fact, not just other things. Many things in your body are optical isomers, as you'll see when I give you some examples. Well, let me just tell you how you would even know this. How do I even know that I have an optical isomer? Called, there are 2 types we're going to talk about. First of all, the optical isomers. All right. How would I even know this? Well, the main way we tell them apart is we put them in a sample, and I'm going to show you a little animation of this. You put the sample, in a container, and you shine a plane of polarized light through it, and it will rotate that plane a certain direction. Now, I'll explain what that means in a second. Okay, write that down first, and you'll understand it in a second. All right, let me show you. First of all, with a little animation here. I'll explain it as it goes along. You want to hit that light for me? Okay, here's my light bulb. Now, light is coming off in waves in every possible direction, if you watch this. Okay, there's waves in every direction. If I put a grating between it with just slits in it, I would filter out all of those except for one plane. One plane now light is going through. And when I pass the light through a sample, turns out that one of the 2 carbone, one of the 2 versions of carbone will rotate that light clockwise, and the other one will rotate it counterclockwise. And that's how you could actually tell the 2 apart. They also have different properties. You say, well, if that's the only difference between them, what's the point? It's not. It is a difference between them. But there are other differences, as we'll see. Turns out that some of the things you do, some of the things you use that are optical isomers, and I have 2 articles to give you on this. If you use the one isomer, it's the drug you're trying to take. All right, it's the one that's going to help on whatever you're having. Most things you're taking, by the way, not most, but a good number of them, of the drugs that you take for medicines nowadays are actually isomers, optical isomers. You can only one of the 2 is the ones you want. All right. Because one of them will be dangerous, the other one will be helpful, or one will be innocuous. All right, you put that backlight on again. All right, let me show you first of all how I could polarize light. All right, I think I'll need a whiteboard here. Let me just do this. Okay, there, nice bright light. See this? It's just a filter. Okay, it's the same kind of polarized lens you might have on your sunglasses, okay? And if I shine that on the board here, see it on the board? All right, it looks kind of greenish. You see the kind of green color you have there? All right, I'll shine this one. And depending on how I rotate it, see how it looks kind of purplish or green? You see that? Now, this is kind of neat. Watch this. If I put them up next to each other, all right, the purple and the green, If I rotate them in the same direction, light still gets through. See, polarized sunglasses are filtering out a good portion of the light, so they don't bother. It doesn't hurt your eyes. The UV light won't, bother your eyes. But watch what happens. I rotate the one across the other one. All I'm doing is rotating this guy, and there you go. It's gone. It blocks it all out. Why? What did I do? I blocked out the one version that was coming, the one plane that was coming through. When I turned it to block that one out with the other lens, I can't see it all through them. You can actually do that with certain sunglasses. If you have polarized sunglasses, you can actually put them up next to each other, rotate them until you couldn't see anything through them. Like you'd have to have the two glasses. You couldn't do it with the same. It has to be more than one lens. But that's what you could do. See that? Isn't that cool? I'll do it again. All right. There it is. See, I keep rotating it. Now they're in the same. They're blocking out the same stuff. If I rotate it, and he's blocking nothing. Can't see anything through him. Isn't that cool? That's kind of neat. If everybody can see that, I hope. All right, good. Even at home, people at home. All right. So that plane, what I do is I put a filter in front of the light source, and I'm only shining one plane through there. And it turns out that if I shine it through this guy, it's going to rotate the light one way. But if I shine it through the other guy, it rotates it the other way. And that's how you can tell them apart. We have different names for these kind. And it's a funny thing about chemistry. This often happens, I think, unfortunately, I remember in college hating this. Maybe they're more systematic nowadays than when I was in school. But there are a lot of different ways to say the same thing. You're going to find out that what you guys know as vinegar you're going to also know as acetic acid or ethanoic acid. All right, and all three of them are used, interchangeably. Okay, they're all different names. And we're going to learn how to name these guys in organic. Well, there's also more than one system to name these guys. All right. By the way, here's what's happening. I'll get to the name system in a second. See, here's your light going through these diffraction grade, or the polarized light. That's what's really in here. It's just basically slits. Okay. All right. You've selected for just one. If I rotate and block that one, that's when that thing turned black completely. Well, I want to have only the one slit going through, and it will rotate the light. All right. So while this is going again, let's get some of the notes on there. We call, again, there's three different ways we actually name these, which I don't like. But you can either call it plus or positive, D. Those kind rotate the light clockwise. If you pass it through the sample and it rotates the light clockwise, you call it D or plus. Notice this one's calling the one that rotates the light clockwise R. That's not necessarily true. R and S are the confirmation or the configurations we're going to use, but they aren't necessarily related to rotating the light clockwise or counterclockwise. All right, D or plus does talk about specifically which way the light is being rotated. If you call it L or negative, it rotates the light counterclockwise. Sometimes the two correspond, sometimes they don't. All right, biology tends to use the L or D, and you may notice, you may have seen that. Anybody have AP Bio? You may have seen an L or a D in front of different compounds, especially in front of things like amino acids. Turns out that all the amino acids that you know from biology exist in two forms. Okay, either a left-handed or a right-handed one. Basically a D or an L. And in your body, you guys only use the S configuration. All right? That's the only ones you use. There's R and S we're going to talk about too. We're going to show you how to do those. All right? The different versions will react differently with optically active compounds. And they will react, that means that we must be an optically active compound. Our bodies, our sense of smell, for example, for the dill, or for the spearmint, are optically active. Because they react differently. We don't smell pickles when we have spearmint. It smells slightly different. But there is that similarity, too. Oh, I said sesame seeds, by the way. I meant caraway seeds. Those are the ones that smell like rye bread. Caraway. In fact, maybe if Mrs. I didn't have any, I could ask Mrs. Nor if she has any caraway seeds. I could crush a couple of them. You'll see what the similarities there too. All right. So that's the ones I used a second ago. Carvone, which is in dill and spearmint, which you did spell. All right. Thalidomide, which you have an article to read about, and most amino acids. I said all. I think not every amino acid. Most amino acids exist only in the S configuration in your body to make those proteins. That's what they use, right? Amino acids are used to make proteins, right?
Yes.
You remember that from bio, I hope. Now, after you copy that, I've got 2 articles I want you to read, and I also want to go over. I'm actually not going to do the new notes for tomorrow. I want to kind of do them one day. That's a double period. Today is a single, right?
Yep.
Yeah, and the double period is a better day to do that. So here's what we're going to do for the rest of this period. I got 2 things I got you to read. Remember how in the last test I had questions mainly on the greenhouse effect, and then also on the climate change, global warming. And there were 3 essay questions on that. Well, I'm not saying there'll be 3, but I think there's 2 on this one, short answer questions on these articles, and another one we're going to do on trans fatty acids, okay? Remember unsaturated and saturated fats. So it'll be on probably one of these 2 things. I think that's all there is. I don't know if there's another one to give you, but there'll be at least articles on those 2 things that you'll have an essay question on. So I'll give you those now. But actually, I'll give